that beat. Juju on that beat. Juju on that, juju on that, juju on that beat. Now slide, drop, hit them for no stop, ayy. Don't stop, ayy.
We'll finish this lecture by discussing an example that we talked about at the beginning of the lecture. Let's take L to be the field generated over Q by square root of 2 and square root of 3, and K to be Q. L is a splitting field for the polynomial x squared minus 2 times x squared minus 3 over Q. So we know that the number of automorphisms of L fixing K, the number of automorphisms of Q adjoint square root of 2, square root of 3 fixing Q, is the degree of this extension, which we know is 4. This is an extension that we've discussed quite a lot earlier. So at the beginning of this lecture, we saw that any sigma in this group of automorphisms of L fixing K is determined by where it sends square root of 2 and where it sends square root of 3. And that we don't have many options. That sigma of square root of 2 has to be square root of 2 or negative square root of 2. And sigma of square root of 3 has to be square root of 3 or negative square root of 3. So there are 4 total choices, because I have 2 choices for where to send square root of 2 and 2 choices for where to send square root of 3. It is not obvious that each one of these choices actually gives an automorphism of L. But because we know that the number of automorphisms of L fixing K is 4, and we only have 4 possible choices here, we conclude that each one of these 4 choices must actually give an automorphism of L fixing K. All right, so what are these 4 elements? One way to ask this question is, we know that we have this group of order 4. What group is it? So now I'm going to switch notation a little bit, and instead of talking about a general element sigma in aught L over K, we'll pick sigma to be the particular automorphism given by the one that fixes Q, sends square root of 2 to negative square root of 2, and sends square root of 3 to square root of 3. And tau is going to be the automorphism that fixes Q, sends square root of 2 to square root of 2, and square root of 3 to negative square root of 3. Okay, but what does that really mean? Like, what does sigma do to an element of this field generated over Q by square root of 2 and square root of 3? Well, every element of that field looks like a plus b root 2 plus c root 3 plus d root 6, where a, b, c, and d are rational numbers. So what does sigma do to such an element? Well, it fixes a, it fixes b, but it sends square root of 2 to negative square root of 2. It fixes c, it fixes square root of 3, and it fixes d, but it sends square root of 6 to negative square root of 6. So this element gets sent to a minus b root 2 plus c root 3 minus d root 6. What does tau do? It sends a plus b root 2 plus c root 3 plus d root 6 to a plus b root 2 minus c root 3 minus d root 6. Okay, it is clear that if you compose sigma with itself, if you do sigma twice, then, well, what does it do to square root of 3? It sends square root of 3 to itself, then it sends square root of 3 to itself again. It sends square root of 2 to negative square root of 2, but then it sends negative square root of 2 to negative square root of 2, which is square root of 2. So it sends square root of 2 back to itself. So you do sigma twice and you get the identity. Same idea, you do tau twice, you get the identity. What happens if you compose them? If you first do tau and then do sigma? Well, if you first do tau and then do sigma, what does it do to square root of 2? Tau sends square root of 2 to square root of 2, and then sigma sends square root of 2 to negative square root of 2. So this composition sends square root of 2 to negative square root of 2. Tau sends square root of 3 to negative square root of 3, and then sigma sends negative square root of 3 to negative square root of 3. So sigma tau sends square root of 3 to negative square root of 3. Okay, so this is the other automorphism of L fixing Q. It's the one that is not the identity sigma or tau. You do this twice, and for the same reason as before, you get back the identity. So what are we seeing? We're seeing that we have this group of order 4, the Galois group, of Q adjoins square root of 2 and square root of 3 over Q. It consists of these four elements, these four automorphisms of L fixing Q, the identity, sigma, tau, and sigma times tau. And the three non-identity elements have order 2. So this group of order 4 is isomorphic to Z mod 2Z cross Z mod 2Z. Okay, so this is our first example of computing a Galois group with this language of what it means for an extension to be Galois. So I'm going to pause and erase, and I'm going to talk about one additional thing that we could ask. So remember, part of what we're trying to understand is this correspondence between subgroups of this group aught L over K, or in this case, the Galois group of L over K, and subfields of this field L that contain K. So in this case, subfields of Q adjoins square root of 2 and square root of 3 that contain Q. One of our major goals is to understand the relationship between subgroups of this group aught L over K, or in this case, the Galois group of L over K, and fields, subfields of L that contain this field K. So for each subgroup of this Galois group, we can determine the subfield of L containing K. So in this case, the subfield of Q adjoins square root of 2 and square root of 3 containing Q that is its fixed field. So let's do an example. Right? So remember, sigma is this automorphism that sends square root of 2 to negative square root of 2 and square root of 3 to square root of 3. So we saw how it acted on an element a plus b root 2 plus c root 3 plus d root 6. It sends it to a minus b root 2 plus c root 3 minus d root 6. So what does it mean for an element in L to be fixed by sigma? Well, if the coefficient b is not 0, this is not fixed. If the coefficient d is not 0, this is not fixed. So the fixed field of this subgroup, the set of all elements in L that are fixed by all of the things in this subgroup, consists of all of the elements of L where b and d are 0. So what do those look like? That's all the elements of the form a plus c root 3, where a and c are rational numbers. And this is Q adjoins square root of 3. Okay, so you can do something very, very similar and see that the fixed field of the subgroup, for example, the identity in tau, is Q adjoins square root of 2. And the fixed field of the subgroup, the identity and sigma tau, is Q adjoins square root of 6. And okay, these two are clear that the fixed field of the identity subgroup is all of L, and the fixed field of the entire group of automorphisms of L fixing Q is just Q. So the last thing that I want to do is write down this diagram showing these fields. So L at the top, K at the bottom, and then subfields in between L and K. And then write down this Galois group at the bottom, the identity at the top, and this diagram of subgroups of this Galois group. And what I've done is drawn this diagram in such a way that every subgroup is in the same place that its fixed field is up here, that there's this kind of symmetry, but there's this correspondence that you can see in this diagram. So this is the kind of thing that we're moving towards understanding in general, this correspondence between subgroups of the Galois group and subfields of L containing this base field K.